Okay.
Our next speaker is Edoardo Colombo, who is going to talk about holography with conical singularities, black hole entropy from SCFT on the spectrum.
Hello, everyone. Today I will talk about some work they've done in collaboration with Hosseini, Martelli, Pitelli, and Zaffaroni. So we'll know that semi-classically, the entropy of a black hole is proportional to the area of the event horizon, but we would like to reproduce this by counting the black hole microstates. So for supersymmetric black hole in anti-de Sitter, we can count the BPS states of the dual SCFT. And there's a very famous work by Benini, Hristov, and Zaffaroni, which this was first achieved for a class of anti-de Sitter 4 black holes by taking the large n limit of the topologically twisted index. We will work on a similar problem today. We will also consider IDS4 black holes, but we will have orbifold conical singularities to deal with. And we will reproduce their entropy by taking the large n limit of the spindle index. Our result will be the first such holographic correspondence involving CFT on an orbifold. So, plenty of people have talked about these black holes already, but let me be brief. The horizon geometry is IDS2 times the spindle. I think people are already aware what the spindle is at this point, is this. There's a key fact is there's a spindle also at the horizon times the time direction, which means that the dual CFT lives on the spindle. Again, all these conical singularities disappear when one takes the uplift to 11-dimensional supergravity. And as already mentioned in talks on Tuesday, this describes accelerating black holes. So the spindle index of n equal to Chern-Simons matter theory is the supersymmetric partition function on spindle times S1. And there are two ways to preserve the supersymmetry, and they are distinguished by the flux of the R-symmetry background. You can either have, here, this sigma is a sign. If this sign sigma is +1, you're going to have the twisted spindle index, which in the limit where the spindle becomes a sphere becomes the topologically twisted index in 3D. On the other hand, if sigma is equal to the -1, this is the anti-twist, and in the sphere limit, it becomes just the regular 3D superconformal index. Okay, so the index has been computed by supersymmetric localization by Inglese, Martelli, and Pitelli. Schematically, this is going to be given by a sum over gauge fluxes, an integral over gauge holonomies, of an integrand, which is a classical piece, which is the action evaluated at the BPS locus, and one loop determinants. Now, before I give you the expression of the integrand, let me set the stage a little bit. This integrand can be factorized as a product of two holomorphic blocks. Each holomorphic block, which I call B plus, B minus, plus and minus, by the way, refer to the two poles. These two holomorphic blocks correspond to the partition functions, roughly correspond to the partition function on the half of the spindle. And these holomorphic blocks depend on various chemical potentials and holonomies and fluxes. Let me introduce them. There's omega, which is for the angular momentum. We have the gauge holonomies and gauge fluxes, which we package in these zeta variables. And there's the holonomies and fluxes also for the flavor and topological symmetries, which we package in the delta plus or minus variables. But so far so good, but there's a new ingredient, which is kind of unique to the spindle, and it is fractional terms, which we denote with a curly A plus or minus. So let's explain these curly A's. First, let me introduce the fractional fluxes L plus or minus, which are given by a coefficient times the gauge fluxes modulo n plus or minus. And these fractional terms are given in, depend on these fractional fluxes plus some flavor terms modulo n plus or minus. So, what's the deal with these curly A's? The deal is that in the large n limit, we would like to take continuum limits. But these curly A's are an obstruction to taking a continuum limit because they cannot be packaged into a continuous function, or as we will later see. So what do we do with them? The key idea is that we want to write the index in this form. We want to write this as two integrals, one for each holomorphic blocks, but we're also left with outside a sum over these fraction fluxes L plus or minus. These integrals, we will deal with them by usual saddle point approximation, but what do we do about this piece? So what we do is that the idea is that when we have a sum over a lot of contribution that are exponentially growing, it is expected that one should dominate over the other. This is an expectation one can have. And so what we have to do is we must determine which is the dominant value of this L plus or minus, and these dominant values would be plucked at when we do the relative computation. Okay, let me flash briefly an expression for the blocks, plus or minus. Without going too much into details, I can say that there is a contribution coming from Chern-Simons terms, a contribution coming from topological symmetries. Both of these are classical contribution. And then there's one loop terms, which is given in terms of cupocammers. Okay, but instead of focusing on every little detail of these formulas, let me show what is different from the case of the sphere. Well, for the spindle, of course, we're going to have the curly A's, as already anticipated. But another difference, which is going to be important later, is that for each term, for each superpotential term, there's going to be a constraint on these delta plus or minus, which are the flavors of the Carrolls. And it contains the spindly n plus or minus, which are the orbifold integers at the poles. Okay, now a technical detail, which is going to be important. For adjointed by fundamental matter, we have products over two indices ij that go from 1 and to n. And when you have these products, we have to split two contributions. The terms near the diagonal are called shorting contribution. Leading order, they usually come from they only come from the cupocammers. But we also have these long-range forces, which are the terms that are far away from the diagonal. And these terms must vanish in order to be able to apply all the known methods for computational large n limits. So we focus on simple, non-chiral Chern-Simons quiver theories with a 3D analog of the 4D anomaly constellations. But for the purpose of these slides, I'll just mention a BJM, which I hope everybody's familiar with. So we compute for these theories the long-range forces, and the expression that we find is not particularly illuminating, but this is an expression that must vanish if we want to be able to apply the methods of large n computation. And we can see, well, there is, from this we can find that there is a special ansatz for the fractionate fluxes that makes these long-range forces immediately vanish. And this helps us single out a special ansatz we're in desperate need to do the large n computation. Okay, so now that we have our answers for the fractionate fluxes, the rest of the computation is somewhat similar. We want to take a continuum limit, which means that indices that go from 1 to n are replaced with a continuous parameter t, but there is also a discrete index that is left over, which is, by the way, matches the L plus or minus for our ansatz. Okay, so sums becomes integrals over t with a eigenvalue density distribution, but there's also this sum. And how do we deal with the sums? Actually, there's a relatively simple formula that gives the sums of the powers of these fractional terms, any power, with a very simple result. So we can easily deal with this piece. And the rest is actually very simple to the sphere case. So let me jump to the result that we get. We get that the product of the two holomorphic blocks is given by these sum of these free energy at the two blocks. And this free energy is, of course, a function of the rho and this function y that appear in the ansatz for zeta. And the upshot is that these expressions are exact same that one encounters in the sphere case. So there's nothing spindly in here. What is spindly is, of course, that the constraint over the deltas is different from the sphere case. So, okay, we need to fix rho and the function y. For a BGM, it's just the difference of the two functions y at the two gauge nodes that matters. And the externalization works out more or less in exactly the same way as the original paper by Benigni, Riesel, and Zaffaroni. And the result of this externalization procedure is these two functions for, this is the graph for rho, and this is the graph for the difference of y's. So when we plug these results into the free energy, we get this very simple result, and this gives us the final result for the computation of the Lagrangian limit of the spindle index, which is written in terms of sum of two gravitational blocks in the gluing given by sigma. And this perfectly matches the entropy function of the spindle black holes. What does this mean? This means that if one takes the Legendre transform of this expression above, one recovers exactly the exact expression as the area of the event horizon of the spindle black hole. So, this concludes the first holographic matching involving CFT on an orbifold. But what about some higher dimensional steps? Well, I want to briefly mention some ongoing work about IDS5 black strings, which are dual to torus times the spindle. How much time? Okay. Okay, so these black strings have IDS3 times spindle or BTZ black hole times spindle near horizon. Again, plenty of people found some solution that have a smooth 10-dimensional uplift. And the localization computation has already been done for this, for the T2 times spindle. And the upshot is that in the cardinal limit, one needs to find, we expect to find the density, the entropy density of the black string. And our progress so far is that the Lydian n-squared order, we have nailed it down perfectly. There's still some work in progress regarding the sub-Lydian and to the zero order, and some technical details about even for these black strings, the twist and twist, but the anti-twist background is still a bit mysterious, and there are other technicalities that I will not mention. So let me conclude. This conclusion slide is very similar to the conclusion slide of Dario's talk, but it's the same project, so can't do much about it. There we could enrich the 3D computation with maybe considering lower corrections, extending to broader class of quivers, if possible, because it's not known if, how to. Of course, I mentioned that DS5 black strings, but of course there are possible other setups, maybe involving even different orbiflows than the spindle. So thank you, and I'm done.
Thank you. Questions?
I have a question. What's the physical interpretation of the curly A parameter that you introduced, I think, on slide 7?
Physical interpretation.
Is it related to the acceleration of the black hole?
No, the acceleration is just related to n plus or n minus. It's not related to these fluxes. I don't really have a illuminating answer. Maybe it's something to investigate, but for our solution, it gets averaged out, essentially. So maybe if one wants to find an interpretation, maybe holographic, one will need to consider different ansatses to see what's the difference, but they become complicated, and this is all I can say.
Hi. So you talked a bit at the end about going up to spindle cross T2, but what about going down to just spindle? Is it very easy from your calculation on the three-dimensional to just read off the large n limit of the spindle index, or is there any other subtlety?
I haven't tried to. Honestly, I was working up rather than down dimension.
Right. I guess I could rephrase it as, is the S1 doing anything special in the calculation, or is it just coming along for the ride and all of the interesting new stuff?
I think it should be possible to take it and reduce it, but because as a check, we took the torus stem spindle and reduced on S1 to check if it was correct. So that was doable, and but we had to be careful about singularities, and so it's a bit tricky. But it technically should also be possible to maybe I don't know, I haven't tried to take and reduce along this one.
Okay, thanks.
I have two things, but maybe there's no time. About the curly A question, is it possible they're related to the possible holonomies the possible holonomies around the spindle at each pole that are imposed by the spindle structure? Just because you mentioned that they're related, you are summing over Zn.
Sorry, I don't know. I'll have to think about it more a bit. Maybe for to discuss it is interesting question.
Very brief comment. Those are just essentially the fluxes of the gate. They incorporate the fluxes that the series was talking about.
And the other question, is it possible to use similar techniques to calculate similar indices for other theories for other fixed points in 3D and 4D theories such as the Lee-Stressler and MADJM theories?
These techniques about these, I didn't mention because I was short on time, but this is very, very similar to the to something that one encounters when dealing with the large n limit of the superconformal index in 4 dimension. The beta ansatz formula for the superconformal index in 4 dimension involves similar sums in when the angular momenta are different than one another. This is something I spent quite some time to think about in my master thesis and beginning of PhD. And in that case, actually, the answer was almost identical to this case. We need, in order to get the proper Largen limit of the superconformal index, one needed to take an ansatz which is almost identical to this one. So, so possibly there are also other problems that might actually be solved with the similar strategies, for sure.
Can I ask one question?
Yeah.
Can you push this beyond leading order?
Well, the expert on pushing beyond linear order is Bobev here. I think they're very complicated computation even in non-spindle case, but definitely something that we might want to try at some point.
Pascal, last question.
Yeah, so this L that you fixed to this special ansatz, previously you said that you need to like extremize, like choose the leading, like you said something from the lines of that L, you have to select it such that you pick the leading saddle. So how is this related to this this simplifying ansatz? We simplified it, so I got confused how L is fixed.
Well, it's actually very simple. It's without canceling these long-range forces, we actually cannot make any progress with the known methods of large-end computation. So this is a kind of forced choice, and it actually works out perfectly. But since the lack of long-range force is actually something physical that's seen even in the S3 case, it's maybe not surprising that the choice that automatically cancels is also the choice that should be holographically selected. But I can't say anything more profound, sorry.
I think we should stop here. Thank our speaker again.